Okay, so I promised examples for Fourier Cosine Series and Fourier Sine Series. So let's give you an example of find the Fourier Cosine Series of f of x equals to x plus 2 on 0 to 4. So let's try this question. But before I actually do the calculation, let's see what it means. So on 0 until 4, there's the graph y equals to x plus 2. So here's 2, and then when you plug in 4, it'll be 6. This will be 6. And then, because you're looking for the cosine series, what it really is doing is you take this function and you extend it as an even function, so that when you fold it over the y-axis, it evenly matches, so that you have a function from -4 to 4, and you're taking the Fourier series of this. And because Fourier series formula a0 equals to 1 over 2l from -L to L of f of x, and since this is this fx is an even function, instead of integrating from -4 to 4, you can just integrate from 0 to 4 and double that result, right? And although you feel like you still have to do some integral, it doesn't feel like anything better. But in practice, it does significantly reduce the amount of calculations, so you really want to use this formula instead. So instead of this formula, when f of x is even, you want to use this formula, okay? So that's what we're going to use for a0. And then for an, we have 1 over L, -L to L of f of x, cosine of n pi over Lx dx. And then, again, for the same reason, cosine is an even function, fx is an even function. If you multiply two even functions, you get an even function. So, again, you do the trick of integrating only on the half interval, and you double the result. And then finally for Bn, 1 over L, -L to L f of x, sine n pi over Lx dx. And because fx is even and sine is odd, if you multiply odd times even, what do you get? Odd. So if you integrate, what do you get? 0. So that's a 0. And therefore, in the Fourier series formula, where once you get these values, f of x equals to a0 plus summation of n equals to 1 through infinity of an cosine n pi over Lx, and then plus bn, and then sine something, but this one's gone because bn's are 0. And that's why this is called the Fourier cosine series, because you only see cosines. Okay. So that's the context of the problem. Now let me actually use these formulas to calculate. But in order to use this formula, we actually have to know what L is, right? What's L for us? 4, right? Because it's from 0 to 4, and this is for 0 to L. So our L should be 4. So that's what we're going to use for calculating. A0 is equal to 1 over 4 integral from 0 to 4 of x plus 2 dx. And that's going to be 1/4 of 1/2 x squared plus 2x. And you have to plug in 4 and 0, which gives you 1/4 of 8 plus 8. And that's going to be 2 plus 2, which is 4. And by doing this doubling trick, not only you got to plug in 0 for one of them, giving you one less thing to worry about. If you couldn't use this trick and you're forced to use this, then you really have to figure out what this side is. Okay? Now, if you're curious, I can write down the actual even extensions of f even. I'll just say even for f even extension would be x plus 2 if x is positive, and you would get negative x plus 2 if x is negative. Now it would be a piecewise function, right? See, this red line here has about the same slope, right? But with a negative. So it's positive. If this slope is positive 1, this might be negative 1. And they have the same y-intercept, so 2 doesn't change. So that's what I wrote down. So if you have to do it this way, it'll be a lot more complicated because you have to use this formula for one integral from -4 to 0, and this one will be what you use for 0 to 4, and it's ugly. You don't want to do that. So doing it this way is much better. Okay. Now let's try an. An would be 2/4, 0 to 4 of x plus 2 cosine n pi over 4. Remember, L is 4, so this becomes 4 here, dx. And as I explained last time, you do end up having to use the integrate by parts many times when you do Fourier transform or Fourier series. Because you do it so many times, it's a lot easier if you know a trick that makes it faster. And that trick for me is the tabular integration. So the tabular integration, let me show you how to do it for the cosines. So you have plus minus d integral. You do have to memorize some stuff. Initially, that's the confusing part. You have to make sure that the first part is the sine, and the second column is the derivative, and then the last one is the integral. If you switch these around, then the tabular doesn't work, then you'll be in trouble. Okay. All right, and then I put x plus 2 here, and put cosine n pi over 4. And I know from this thing called V8, where cosine is trigonometric and x plus 2 is algebraic, so x plus 2 should be the one that's differentiated and t should be the one that's integrated. Okay, so that's that's what we have, and then keep differentiating until you hit 0. And this one you have to integrate, and hopefully you know how to integrate this one. See, if you have any coefficient in front of x, the reciprocal of that number appears in front. So n pi over 4, you take the reciprocal, then you flip it upside down. It's 4 over n pi. That appears in front. Integral of cosine is? Sine, thank you. And then you have sine of n pi over 4x. And then, integrating this again, another 4 over n pi will appear, so it will be 4 squared, n squared, pi squared, and sine integrates to negative cosine, n pi over 4. And then I stop here because this became 0. Okay. The tough kind of integration of parts is when this doesn't become 0, But the nice thing about Fourier series is that usually you end up with the things that do give you 0. So most likely you're going to get problems like this. Okay? And then you put plus, and then minus, and then plus. And now you have to collect the results from here. It's not straightforward. You have to do it this way, like a boy throwing a rock. This, that, and then go down 1. Okay, yeah, it's like that. So if we have that, the result is that you have. Don't forget this 2 over 4. That's like the most common mistake people make. If they have some coefficient in front and they're so worried about the integral, they forgot that there was a coefficient in front. So don't forget that one. And then the integral of this result is there, which says it's x plus 2 times 4 over n pi sine n pi over 4x. And then negative times negative is positive, so it's plus 4 squared, which is 16. 16 over n squared pi squared cosine n pi over 4x. And then you plug in 4 and then 0. Okay. Now, there's another very common thing that you will see when you calculate Fourier series is you get sine of n pi and cosine of n pi. Okay. What's sine evaluated at integer multiples of pi? Can you remember the picture I drew for the sine? Yeah, 0, right? 0, pi, 2 pi, 3 pi. It'll always be 0. Even like here, the negative pi, it'll always be 0, right? How about cosine n pi? What happens there? Cosine graph, remember? It's like that. So here's 2 pi, here's pi, here's 0, here's 3 pi, 4 pi. What's happening?
Negative 1. Is it negative 1?
It's cosine pi is negative 1, but cosine 2 pi is positive 1, right?
Yeah.
And what's happening afterwards?
It's going back down.
Coming that, yeah, it's going up and down, right? How would you write that easily?
Plus or minus 1.
No, not that way. There's a better way.
Negative 1 to the n.
Yes, negative 1 to the nth power. Okay. So that's how you want to write your result. And by the way, we did something similar yesterday, which was e to the I n pi, right? E to the I n pi, I explained that, well, this is same as e to the I pi to the nth power, because if you multiply these two, you get that, right? Well, what is e to the I pi? The most beautiful equation in math? Negative 1, right? So e to the I pi is negative 1, and you end up with negative 1 to the nth power. But if you think about what this is, what is this? This is, by the Euler's identity, it's cosine n pi plus I sine n pi, right? So you look at this, what's the real part of this number? This itself, right? So cosine n pi is the real part. What's the imaginary part? Do you see any I? Nothing. So 0i is what you have, and that should be the value of sine n pi, right? So that's another way you can figure out that sine n pi should be 0 and cosine n pi should be negative 1 to the nth power. Okay? So hopefully with these two explanations from the graph and also from the Euler identity, you can remember that this is true. So that's what I'm going to use, because look, when I plug in 4 into x, what's happening? 4 cancels, right? So 4 plus 2, 4 over n pi, sine of n pi over 4 and 4, they cancel away, and what do you get? Sine n pi. What's that? Sine n pi is? 0. And you get n squared pi squared. This time you get cosine n pi over 4, and 4 is plugged in. 4 is plugged into x, right? And again, you get cosine n pi as a result. And what do you get? Cosine n pi is negative 1 to the nth power, right? And then when you plug in 0, you get 0 plus 2, 4 over n pi sine of 0 plus 16 over n squared pi squared cosine of 0. And from our discussion, we know that sine n pi is 0, so that's 0 because this is 0. Sine 0 is 0 because that's like sine n pi with n being 0, right? So sine 0 is 0. Cosine n pi is negative 1 to the nth power, and cosine 0 is, well, it's like cosine 0 pi, right? Cosine 0 pi. If you plug in negative 1 to the 0th power, you get positive 1, right? So that will be 1. So the end result is that you have 16 over n squared pi squared negative 1 to the nth power minus 16 over n squared pi squared times 1. And because these are all common, you can factor it out. 16 divided by 2 is 8. So you end up with 8 over n squared pi squared of negative 1 to the nth power minus 1. Okay. Okay, so we got the A0, we got the AN. Do we need BN? No, because this is asking for Fourier cosine series. So we're thinking of our function as an even function. Okay. So the final answer would be, is that x plus 2 is equal to summation of, oh no, not that one. A0, it should be appearing first. So it's 4 plus summation of n equals to 1 through infinity of 8 over n squared pi squared negative 1 to the nth power minus 1. I need more space, so forgive me if I'm going above, beyond the boundary. Those with OCD might be suffering right now because what I'm doing. Right, so you have cosine n pi over 4x. So that's the answer. This is the answer.
I have a question.
Yes.
So with the 8 over n squared pi squared, how did you get that from 16 to 16?
Right, so you see this 1/2, right? 1/2 times 16 means same as 16 divided by 2.
Yeah.
And that gives you 8, right?
Okay.
Then when this 1/2 is distributed, they both become 8 over n squared pi squared. And since they're common, I can factor it out. If I factor it out, if I yank them out, the things that are remaining inside the parentheses are these two items. Okay? All right. So that's our answer. That's the cosine. When is this valid? When is this valid? What do you think? Is this true for all values of x? 0 to 4. Okay. If you plot this, and you plot x plus 2, you'll see that these two functions agree between 0 to 4, but then they're going to be different after 4 and before 0. Okay? Now, let me add a bit more about that, because I said I'm going to skip the proof for the convergence of the Fourier series. I have other more interesting stuff than the proof, so I just want to skip that. But what you need to understand is that these functions, cosine n pi over 4x, those are functions that have whole periods inside negative 4 to 4. So cosine 1 pi over 4x or just pi over 4x, this will have the period from -4 to 4. So just to reiterate what I explained yesterday, multiplying by squashes everything, and because just cosine x, this is cosine x, and it's one period from -pi to pi. Periodic means that it's repeating, right? So if you want the full graph of this thing, what do? You select this much, and you do Control C, and you do Control V, Control V, Control V, and then you do Control V, Control V. Mac users have a problem with this? You guys need Command, right? Okay. So either Command V. You know what I'm saying?
Yeah.
Okay, good, good. All right. So I'm saying it's repeating, right? Yeah. I mean, you do that all the time when you do essays, right? Just joking. All right. Yeah, it's just repeating itself. Okay. And then, so what it does is when you multiply by pi, it squashes it so that it's from -1 to 1, and then dividing by 4 makes it expanded so that so this graph will have one period from -4 to 4. So just like that. But then this is not the only one. There are other ones, right? So you have 2 pi over 4 and 3 pi over 4 and all those. These are simply are the ones that have higher frequencies of this. So for example, if you have 3, what it does is that you end up having 3 of these inside here. So you have 1, and then 2, and then 3. Okay, so it's a very high frequency, so it's hard to draw, but that's what you end up with. Okay. In other words, all of these functions that I'm adding have some multiples of its period fitting exactly into this interval -4 to 4. All right, that's what's being done, and therefore, when you add them up, this resulting function will still have the period from -4 to 4. If you draw the graph from -infinity to infinity, you'll see that the graph still has the period from -4 to 4. You just copy the graph that you see from -4 to 4. Of course, it has very high frequency, so I don't know what the shape might be. It should be some weird thing. But you take that portion and you just copy and paste it this way, and that way you'll get the entire graph. Okay, so this will be periodic from -4 to 4. Okay, and not only that, constants are even. Okay, even odd constants are an even function. Okay? So 3 is even. Remember that. Okay, 3 is even. All right, so 3 is even because 3 is a constant function. Constant functions are horizontal. It's symmetric over the y-axis. Okay, so if you have a constant, that's an even function. Cosines are even function. If you add even functions, then it's even. So what you have is, if you had no idea that this is equal to this, and you were just given this, even with that, you still have some idea of what the property of that graph should look like. It should be something that's periodic from -4 to 4, okay? And it's an even function so that the left side is same as the right side. That much will be always true when you have this Fourier cosine series, okay? Now, what does that mean? Well, what that means is that once you know that this is exactly equal to x plus 2, that means if I were to draw this right side from -infinity to infinity, here's what's happening. First of all, I know that it's an even function, so that graph should be this one. And then secondly, I know that it's a periodic function, so this should be repeating. So and so. Okay. So you just go left and right to infinity. That's what the graph would be. Whereas the original function y equals x plus 2 would be like that. Okay? All right. Now, then I'm ready to talk about the convergence of the Fourier series. So the basic idea is that so theorem Fourier series converges at every point of continuity, okay, and at jump discontinuities, it converges to f of a minus plus f of a plus. So it's like this. Suppose it's not this one, but let's say you try to do a Fourier cosine series of a function that has a jump discontinuity. It's like this. So it's like this, and then it's an open circle, and there's a closed circle here. So the value jumps. Okay. Then if you do the Fourier cosine series of this part, well, Fourier cosine series means you only take this right side. Then the Fourier cosine series will still converge exactly at these points, but at this point it's going to converge to this point here in the middle of the jump. Oh, sorry, we're just at half. Forgot. Okay, so it converges to the middle point of the jump. That's the theorem. Okay, that's the theorem I'm not proving. Okay. Yeah, but the important part is that the Fourier series does converge exactly to the function if it's a continuous function. That's quite surprising because for Taylor series, do you have Taylor series for any function? What's the requirement for a Taylor series? Remember how we obtain Taylor series. Yeah?
It needs to be differentiable.
Yeah, because we have to differentiate both sides. We need the function to be differentiable. So, does continuous imply differentiability? No. It's the classic example is like V-shaped function, right? It's not differentiable here. So, if you try to use Fourier series to approximate this, it's not going to work. Okay. On the other hand, so the Taylor series can now approximate this, but you can use Fourier series to approximate this. Okay. So you might think, well, Taylor series looks all nice and easy to do. Fourier series, on the other hand, you have to do integration. It seems ugly, but in practice, it actually gives you a better result because it works even for functions that are not continuous. If you have jump discontinuity, it converges in most cases, but at the jump, it just converges to the middle of the jump. Okay. All right. Now, let me do another example. This time, Fourier sine. So, example 2. Find Fourier sine series of, let's say, f of x equals to 3x squared on 0 to 2. Let's try this. Okay, the Fourier Sine Series treats the function, here's the function 3x squared. 3x squared itself is an even function because it folds evenly, right? However, we're trying to extend this as an odd function. Odd function means you flip once and flip again, right? And the resulting other side would be something like this. So that's going to be an odd function, and we want to find the Fourier series of that. And because it's an odd function, a0 and a_n's will be 0, so we don't have to care about those. We will only need the bn. The formula for bn was 1 over L from negative L to L f of x sine n pi over Lx dx. And using the fact that fx is odd and sine is odd, odd function times odd function gives you an even function. And therefore you double this result and make the integral from 0 to L. Okay. Don't forget to change the interval as well. It's not just doubling, the interval must change as well. And then f of x sine n pi over Lx dx. Okay, so let's continue. So solution. For this, we need to calculate bn as 2 over, what's our L this time? 2. Right. From 0 to 2 of 3x squared sine n pi over 2 x dx. Okay. Oh, so that's nice. This just cancels away, so we don't have to worry about the coefficient outside. We just have to do the integral. Again, it's tabular. So let's write down d here and put 3x squared here, and integral here, and sine n pi over 2x. 3x squared differentiates to 6x, 6x differentiates to 6, differentiates 6, you get 0, and then you stop. Sine integrates to, let's see if you can do this one. Sine. What is it?
Negative cosine.
Right, but then what else?
Or 2 over n pi.
Yes, so you get 2 over n pi because the reciprocal of the coefficient of x appears. And sine integrates to negative cosine. And then you have n pi over 2x. Okay, what's the next integral?
You get 4 over n over pi.
Yeah, so another n and pi, so you get n squared pi squared. Okay.
And you get
Cosine integrates to
sine.
just sine, and it preserves the minus because cosine just integrates to sine. Okay. Okay. Should we stop here or do we go one more step?
One more.
One more because 0 is here, yeah. So you have to do another one. And sine integrates to negative cosine, so another negative comes out, canceling this minus away, and you get 8 over n cubed pi cubed cosine of n pi over 2x. And then you put plus, minus for the signs. By the way, the sign should always start from plus, okay? This sign column, they alternate plus and minus, but it should always start from plus. Now let's extract the result from here. Multiply, multiply, multiply. And the multiplication result is that you have 3x squared times 2, which is 6x squared, and minus n pi. And then you get cosine n pi over 2x. Then negative times negative, positive, 6 times 4 is 24, so it's plus 24 n squared pi squared sine n pi over 2x. And then 6 times 8 is 48. You have n cubed, pi cubed, cosine n pi over 2x. And then you plug in 2 and then 0. Okay. Now let's continue the result here. Again, because, so remember this, or let me ask, what's sine n pi again? 0, okay. What's cosine n pi? Right? So because of that, whenever you plug in these boundary values for the sine, you will see that in both cases you're going to get 0, right? So 2 plugged in, 2 and 2 will cancel, and you'll end up with sine n pi, which will be 0, right? When you plug in 0, it will again be 0, so that goes away, right? And so you're only going to get some results from this one and here. And when you plug in 2, you're going to get negative 1 to the nth power, right? So let's use that. When you plug in 2, it's negative 6 times 2 squared over n pi, negative 1 to the nth power. And then this one would be plus 48 over n cubed pi cubed, negative 1 to the nth power. Okay. So that's what you get when you plug in 2. Now subtract. Now let's plug in 0. Now this time, even more terms are 0, because when you plug in 0 here, it's 0. Can you tell me why? When you plug in 0 here, you get 0. Why?
Negative 6 times 0.
Yeah, 0 goes in here, right? 0 squared is 0, so this entire thing will be 0. Okay, that's nice. So that's 0, and this is the only thing that's not 0. What's cosine 0? 1. So you end up with 48 over n cubed pi cubed. And then I guess we can simplify this as negative 24 over n pi, negative 1. And these two have the same common factor, 48 over n cubed pi cubed. So let's put plus 48 over n cubed pi cubed, negative 1 to the nth power minus 1. Okay. So that's it. Or is it? Is that the answer?
No.
What's the answer?
Would it be?
What's our goal? Finding the series. Is this a series?
No.
No, not yet. Yeah. We're looking for Fourier Sine Series, right? So the Fourier Sine Series is from the full Fourier Series A0 plus sigma an cosine and then plus bn sine. The an's go away and you just have summation of the bn sines, right? So that's what we need to write down. So f of x, which is 3x squared, is equal to summation of n from 1 through infinity of I forgot this n part to the nth power. Negative 24 over n pi, and then negative 1 to the nth power, plus 48 over n cubed pi cubed of negative 1 to the nth power minus 1. And then you put sine of n pi over 2x. So that's the answer. Yes?
Can you remind us why a and n is not being used here?
So if you look at the formula for an is 1 over L integration from negative L to L of f of x times cosine n pi over Lx dx. Our fx, the extended one, it's extended as an odd function, right?
Yes.
So this is odd, cosine's even. So odd times even gives you an odd function, and if you integrate over an odd function over a symmetric domain, what do you get?
0.
You get 0. So that's why they move up here, okay?
Wait, can you repeat that one more time?
This is an odd function, right?
Yeah.
Odd times even is odd. This is symmetric domain. If you integrate an odd function over a symmetric domain, you get you get 0, right? So that's why it's 0. But here's another way to think about it. Since f of x is the one that we're extending, since this is an odd function, you can't get cosines and constants because those are even functions. Okay? If you have an odd function, you can only get sines. If you have an even function, then you should only get a0 and ans. The bn's should not appear. Okay, so this is not planned, but maybe I should say something about this. But anyways, this is the answer. All good, right? Yeah. And these two sides agree. Oh, okay. So I forgot something. Sorry. Okay. So here's one more thing that you should know. These two sides agree for the values between 0 to 2, right? However, at x equals to 2, this will give you a value that's different from here. Now, why would that be? So let me try to explain that, okay? So let's think about what this right side will produce. At least for this and this, we know that they should be agreeing on from 0 to 2. So this is what's going to be produced. But because this one is an odd function, it should be this. That's an odd function, right? And then for this odd function, once you have this interval from -2 to 2, this is a periodic function, so this is going to be repeating like that. Like that. Right. And from -2 to 2 as an open interval, everything is fine. But what's happening at 2? What do you see at 2? At 2, you get this point right here, which is it's 3x squared, so if I put 12. But on the right side, this will be -12, right? So what's the real value at 2? If you plugged in 2 into this right side, what should you be getting? Yes?
Well, when you get 0, this average of the 2.
Yes, exactly. You will get 0 because the midpoint of the jump will be 0. So if you actually draw the graph of the right side, you're going to get this with the open circle here, 0 at 2, and then open circle here, and it's going to get open circle, open circle, open circle, and you get 0. And that's what's going to be repeating. Okay. So the answer for this is that these two sides agree on 0 until 2, and 2 is not included. Because of that theorem that says that Fourier series converges at every continuous point, but anytime that you see a jump discontinuity, it's going to converge to half the jump, okay? The midpoint of the jump. Okay, but there was another matter that I wanted to talk about. Which is not going to be tested directly, but it's a good thing to know to avoid making mistakes, because if you write something and if you check the evenness and oddness, then you might be able to catch some errors. Like, oh, I'm trying to get a Fourier series of an odd function. Why am I getting an and a0 here? Then it will immediately give you some warning signs, right? So it's good to know these concepts. So let me talk about even and odd parts of a function. And so first definition the formal definition is that a function f of x is called even if f of negative x is f of x. If it consumes the minus away, you call that an even function. And a function f of x is called odd if f of negative x is negative f of x. Now, are all functions even or odd? No, most functions are neither. Okay? Except the ones that we're familiar with happens to be either one, like x to some power functions, or sines and cosines, or even tangents. Tangent is an odd function. So although most functions are neither even nor odd, many of the functions that we do know has these symmetries. And if fx is neither even nor odd, we can write down f of x as the following sum: f of x plus f of negative x over 2 plus f of x minus f of negative x over 2. Now, despite f of x neither being an even or odd, nor odd, you can see that if I call this much, let me just write, if I call this much as g of x, so if I say g of x is f of x plus f of negative x over 2, and let's say I calculate g of negative x. Okay, so how do you calculate g of negative x? Well, it's like this. You just copy this formula down here, but the only difference is that I refuse to write any x's. Okay, so these are just blank spaces where I can plug things in. Okay? And then sometimes I would put extra blank spaces to know exactly where x goes into. Okay, so I do that, and then I write negative x into that blank space. So I know that g of negative x is this thing, right? But what is this? This is f of negative x plus negative of negative is positive, right? And what is that? That would be same thing as g of x, right? If you switch these two around, it's exactly the same as g of x, right? So what is g of x? Is it even or odd? It's even, right? Because g of negative x is the same as g of x. Okay? In the same way, if I call this one as h of x, and if I do h parentheses as f parentheses plus minus f negative parentheses, and then you write in negative x in here, then this gives you f of negative x minus f of x over 2. But this time you can't just flip it like that because there's a minus, right? So you actually have to see that this is same as negative of f of x minus f of negative x over 2. And what do you see now? That's negative h of x, which is odd function. Okay? So what we see is that for any function, you have an even part and an odd part. Okay? Now, there's another straightforward proof. It's not hard. I just don't want to spend time on it. This breakup will be unique. Okay? If you just say f of x is equal to g of x plus h of x, where gx is even and hx is odd, and you break it as another g prime of x and h prime, or g2 of x and h2 of x, then you can show that those two two functions. The even part should be equal to the even, and odd part should be equal to odd. You can, I mean, just a minute of thinking would easily get you the proof. Okay, so so this breakup is even, is unique, and I said that if fx is neither even nor odd, but actually you could do it for any function, right? Except that if fx is already an even function, what's going to happen if you apply this? If fx is already an even function, what's going to happen? Yeah?
The odd part will cancel out.
Yeah, it will be just 0, right? Because f of negative x is the same as f of x, so this will be just 0, right? If f of x is an odd function to begin with, then this will be 0, and this will be itself, right? So that's what's going to happen. So that breakup of a function into even and odd part still makes sense. And in fact, later on when we solve the Laplace equations, this will be a pretty important thing to do because, as you have seen here, when you do the calculations, knowing some function being even or odd saves you time. So over there, the same thing happens. So having some function that's even or odd, it's very, very helpful. And the one function that we are very accustomed to, which is neither even or odd, is the exponential function e to the x. Okay, it causes some trouble when we try to calculate with it because it's neither even or odd. It's not fun trying to do it. So what you do is you take e to the x, and you can break this up as its even part and odd part. Oh, I forgot to mention that. Do you see that actually if you simplify the right side, you get this? You see that? This minus this will cancel away, and this will double, but there's a 2 in the denominator, so this is exactly the same. Okay, so I forgot to mention that. Okay, so any function is equal to its even part and the odd part. So in the same way, e to the x is same as this plus that, right? And you can see that these two will cancel away, and this will double, and it is in fact equal to e to the x. And this formula is exactly from here, and this formula is exactly from here. Now, who has seen this function specifically? This one, first part. What is that called?
Is that hyperbolic cosine?
Yes, perfect. Okay, so this one is called the cosine hyperbolic. What is this one called?
Hyperbolic sine.
Yeah, hyperbolic sine. Okay. And the reason that they call it hyperbolic sine and hyperbolic cosine has very little to do with the geometry, but rather that we learned that cosine of x is equal to e to the ix plus e to the negative ix over 2, right? And then we learned that sine of x is e to the ix minus e to the negative ix over 2I. So this is really cosine hyperbolic of ix, and this is 1 over I sine hyperbolic of ix, sine hyperbolic. So that's their relationship. And what that means is that any trig identity that you know will have a counterpart in here. So for example, we know that cosine squared of x plus sine squared of x equals to 1, right? Well, guess what happens here? Because cosine hyperbolic is basically the same thing as this, but there's a 1 over I there. When you square this, there's a negative 1. So the corresponding formula for hyperbolic would be this will be the corresponding formula. Here's another one. Cosine squared of x is equal to 1 plus cosine of x, cosine of 2x over 2. Okay? What's the counterpart? Cosine hyperbolic squared of x, 1 plus cosine hyperbolic 2x over 2. This time there's no sign change because that one doesn't have anything. I think for the sine hyperbolic you need a minus. I'm not so confident to write the one. I'm afraid I might get it wrong, but you'll see a list of things, and they just have the corresponding thing. So, so the reason that people define these hyperbolic cosines and hyperbolic sines is because they have these evenness and oddness, but on top of it, because of this relationship with the Euler identity, a lot of the formulas that you already know that holds for the trig functions have a counterpart, and sometimes that helps you with the calculation. Okay, so these functions will be something that we will be using when we do the Laplace differential equations. Okay, yeah, we're doing so many things before doing the PDEs. There's so many things that you have to learn before getting into the actual solving of the PDEs. Okay, all right. So the final comment on even and odd is the following. I explained yesterday that sine of x is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. And cosine of x okay, now that you know what even and odd functions are, what do you now see when you see these things? There should be something that stands out now.
So I see odd denominators in the sine and
no. Odd numbers and odd functions are different things. So it's just a coincidence. That's not what I wanted. Anything else? I mean, you should now see something that you couldn't see before. What do you see? You know, I feel like it's so obvious that some of you are reluctant to answer. What do you see?
Will the exponents are odd.
Exponents are odd, right? For the odd function, okay? It's not this coefficient. That has nothing to do with it. When you have x to some odd power, what function is it? X cubed is an odd function. X to the 5th is an odd function. X to the 7th is an odd function. That's an odd function. If you add up odd functions, you get an odd function. So that's why sine x only has the odd parts. The moment you see like x to the 8th, when you're doing calculation of a Taylor series, in here, something would say, oh, my spidey senses are saying that I got it wrong. Something's wrong here because x to the 8th power is an even function and I have an odd function. So that's what you should do. Okay? All right. So this part was not directly what I'm going to put it on the test, but it just helps a little bit. So now let's come back to the main subject. So this time I'm going to do endpoint value problems. Let me write it fully. Endpoint value problems. Okay, so here's a y double prime minus y equals to 0, and y of 0 equals to 1, y prime of 0 equals to negative 1. Let's try to solve this. How do you solve this? Oh, sorry. This is not an endpoint. That's an initial value problem. I need y of 2 equals to 0. Okay. See, the difference is that in the one that I just erased, I had y of 0 and y prime of 0, right? that means all my information is at x equal to 0. That's an initial value problem. Now this one, on the other hand, it's an endpoint value problem because I'm giving the information about y at x equal to 0 and x equals to 2. So it's like information at 0 and 2 at 2 endpoints of an interval. Okay? That's why this one's called an endpoint value problem. Okay? So how do you do this? How do you solve this?
Let me replace y and 2 with y double prime minus y.
Yeah. I thought Calc 4 was a prereq for this, isn't it?
Yes.
So someone should remember. Come on, everyone should be remembering how to solve the ordinary differential equations. Then the PDE is 10 times harder than ODEs. How are you going to expect to solve anything in here if you can't do ODEs? How do you solve this? All right, do you want me to review Calc 4, differential equations? Okay. All right. So we're reviewing ODEs. ODE means ordinary differential equations, where it means that you have the regular derivative, not partial derivative, just the usual derivative. Okay. So I'm looking for a function whose second derivative minus itself gives you 0. And it should also satisfy that the function evaluated at 0 is 1, and the function evaluated at 2 should be 0. And one thing that you have to be careful about is that here, this equal sign is an equal sign between numbers, right? Whereas this equal sign is an equal sign between functions. Okay? And because it's an equal sign between functions, the solution of an ODE must be a function, not a number. Is that good? Function, not a number. Okay. All right. So, so the way you solve differential equation is that you don't solve, you guess. You make guesses. Okay? And I kind of explained in the very first class that rather than honestly solving a differential equation, because differential equations are hard, we kind of approach it in a roundabout way. The way we do it is we first show mathematically that solution does exist, and if it does exist, it should be unique. That's how we approach it. And then if that theorem gives you a solid foundation for solving it, then you just make guesses, and if you by chance get the answer, then that's done, because I know that solution exists and there's only one and we found it. That's the kind of argument that we make. Okay? But you can't be guessing. It'll take infinite amount of time trying to guess all the possible functions that satisfies y double prime minus y equal to 0. So it's really an educated guess, right? You make an educated guess about what the solution is. And the way you do it is you say y is equal to e to the rx. So there's some unknown number r, but just from our experience that somehow a differential equation that looks like this, well actually this is what we call the differential equation with constant coefficients. Okay? So if you have a differential equation with no x's, just y's, with only constant coefficients, in that case the solutions look like this. Okay? That's what we learned in ordinary differential equation. Okay? So if we have that educated guess, if we have that clue, what should we do? How should we find out the r? I mean, I know that this is the form of the solution. How would you know the exact value of r that would satisfy this? Yeah?
You make it like r squared minus 1.
Okay, so that's the end of the story. Then that's what you learned, and you probably just memorized it without really thinking why. Okay, but here I'm giving you the reason why. Okay, yeah. See, the reason that you guys have no idea what you learned in ODE is because you just passed the test. You didn't bother to actually understand what was going on. Okay, so I'm trying to give you the review as well as we are moving forward. And when you learn it from me, I really want you to understand it, because as math gets harder, if you really want to graduate with a math degree, then you better understand what you're doing, not just pass the test, right? Okay, so what you want to do is you just plug it in, because it has to satisfy, right? So what I do is e to the rx plugged into y double prime minus e to the rx equals to 0. And I need to know what value of r would make this work. What do you get if you differentiate this twice? Once, r would come down, right?
Yes.
Twice, another r would come down. So what are you going to get? R squared e to the rx. Minus e to the rx. Okay, now what?
Divide both sides by e to the rx.
E to the rx is never 0. Exponential functions are never 0, right? So you divide both sides by e to the rx, and you get r squared minus 1 equal to 0, whose solutions are r equals to plus or minus 1. Then you plug that back in here, so what do you get? You get actually two solutions. You get y equals to e to the 1x, and y equals to e to the negative x. Are these the only solutions? No. What do you do afterwards?
You have to add constants.
Yeah. And here comes the linear algebra, okay? So this left side is a linear differential equation, and it's homogeneous, the right side is 0. In that case, if you have any two solutions, you can take linear combinations of the two, and it will all, again, satisfy the same equation. Okay? Now, depending on your discipline, if you're more of a physics person, then you've probably heard of this as a superposition of solutions. Okay? So linear combination, same thing as superposition. All it means is you take one constant times the first function, and you take another constant times the second function. Good? That's the solution of this differential equation in general. Okay, now let's actually figure out what makes these work. You plug in y of 0, which gives you c1 plus c2, and that has to equal to 1. And then you have y of 2, which is c1 times e squared plus c2 times e to the negative 2 equals to 0. And if you solve for, let's solve for c2. So if I move this to the other side, and c2 e to the negative 2 minus equals to c1 e to the squared. And if I multiply e squared both sides, and also multiply by negative, you get negative c1 e to the fourth power is c2. Plug that into the first one, and you get the value as c1 minus c1 times e to the fourth power is 1, which means c1, 1 minus e to the fourth power equals to 1. So c1 must be 1 over 1 minus e to the fourth power. And c2 must be e to the fourth power with a minus sign multiplies, so it's negative e to the fourth power of 1 minus e to the fourth power. So those are the values of c1 and c2, and therefore you get your answer as y of x equals to 1 over 1 minus e to the fourth power e to the x minus e to the fourth power 1 minus e to the fourth power e to the negative x. That's the final answer. Okay. So apart from these nasty e to some powers, this question seems very similar to what you've done in the ODE class, the initial value problems, where if you have y prime of 0 given and y of 0 given, then you can solve, you get an answer. It's very similar. It's just slightly more complicated because another value is given. And you might think that, oh, okay, so that there's not much difference difference between an endpoint value problem and an initial value problem. However, there's a very big distinction. Yes?
Like, why did we write before y equals e to the rx? Like, why did we choose that?
Oh, that's an educated guess.
Okay.
Yeah, so you just have to remember that for homogeneous constant coefficient differential equations, e to the rx is the form of the solution.
Okay.
Yeah. So, however, there's a very big difference in terms of the math content, and the big difference in the math content is you don't have existence and uniqueness for an endpoint value problem. Okay. You only have existence and uniqueness for initial value problem. Okay. So when you're given the value of y of 0 and y prime of 0 for a differential equation like this, you can always guarantee that there is a one unique solution. That's always guaranteed. Okay. However, if two different points are taken and the values of the function are given at those two different points, then you can no longer guarantee that the solution is unique, or even that the solution does exist. Okay? So let me demonstrate why. So what I'm going to do is I'm just going to change this ever so slightly. I'm just going to put plus instead of minus. And then I'm going to give different values for y of 0. So y of 0 is 0 and y of pi equals to 1. So let's try this. Now, for this one, again, I can plug in e to the rx in there. And by now, you kind of see what's the result of it, right? If you differentiate twice, you get r squared, right? And if you don't differentiate at all, you just get 1, right? So if you plug this into here and here, and simplify by dividing by e to the rx, the resulting equation is that you have r squared plus 1 equals to 0. And then you get r squared equals to -1, which means r is equal to plus minus I. So what are the two solutions? Y equals to e to the ix, and y equals to e to the negative ix. Right? Now that might have puzzled you very much, but we know Euler's identity, right? So we actually know what this means. It means that this one gives you cosine x plus I sine x, and this one gives you cosine x minus I sine x. Okay. Now, because the differential equation is a real coefficient differential equation, it's a real differential equation. The numbers that's appearing in the differential equations are only real values, right? So what we can do is we can pretend that we plug this in here and there, but then only take the real part of it. If you just take the real part, then what do we get? We get that cosine double prime plus cosine is equal to 0, right? Which, by the way, is true, right? What's the second derivative of cosine? Negative cosine plus cosine should be 0, right? Moreover, the imaginary part should also satisfy the same thing, right? So sine x should also satisfy sine x double prime plus sine x equal to 0, which again, we know to be true. Right? So we, instead of going with the original plan, we change our plan to take the real part and the imaginary part of the solution. By the way, you see that this doesn't give you anything new. It's still the same thing. The real part Imaginary part is negative sign, but that's just the multiple of sine x, so that's nothing new. So now you get two real solutions, cosine x and sine x. And really, these are preferred over the e to the ix and e to the negative ix because those produce complex values and you're trying to solve a real world problem and you have these, that's not going to help, okay? It's not going to cut it. So you really need to take the real part and the imaginary part, okay? All right, so with that, I get that the solution looks like y equals to c1 times cosine x because, times plus c2 times sine of x because I'm taking linear combination of the two functions I got. Okay, I'm taking the superposition of the two solutions. And then now what do? You have to apply the conditions, right? What's y of 0? That's c1 times cosine 0 is what? 1. Sine 0 is 0. And then this should equal to 0, so c1 must be 0. Right? So you just get y equals to c2 sine x. Right? But now what's y of pi? c1 sine pi, and that has to equal to 1, right? What's wrong here? What's wrong with this? C2 sine pi equals 0. Yeah. What's wrong with this? C2 times sine pi equals to 1.
Sine pi equals to 0.
Yeah, sine pi is equal to 0. Right? So there's no way you can have some C2 that will make this work. Right? So can't work. So this example shows that for endpoint value problems, you may not have a solution at all. Okay. That's the problem. Okay. On the other hand, if I were to say, so let me write it here. On the other hand, y double prime plus y equals to 0, y of 0 equals to 0, and y of pi equals to 0, this will actually have infinitely many solutions because for this one, it's exactly the same. You still have y equals to c2 times sine x if you solve it and you plug in y of 0 equal to 0. So this is the only remaining condition. Let's see what happens when you try to apply this condition. c2 of sine of pi equals to 0. What's the value of c2? Can this happen?
No.
Yes, it can. This can happen, right?
Okay.
For what value of c? c2? Anything, right? c2 can be 3 or 4, any number, because sine pi is 0, any number times 0 is 0, right? So this is true for any number c2. Therefore, solutions are y equals to c sine x with any c, which means infinitely many solutions. Okay? So that's the big difference between an initial value problem and an endpoint value problem. Okay. Now it turns out that there are some class of endpoint value problems that we are very interested in. So consider y double prime plus lambda y equal to 0. With y of 0 equals to 0 and y of some L equals to 0, where L is not 0, so it's like 2 points, 2 points. if this EVP has a unique solution, then y must be what? Oh, that's a very easy, tricky question. It's really hard if you try to think of a solution, but if you know the answer, it's like really easy. Try to answer that. Let's see who can answer this question. Okay. If this endpoint value problem has, if you know that it has a unique solution, then we actually know what that answer should be. Let's try something. Anyone? Yeah?
Just y equals 0?
Yeah. Y equal to 0. Let's see why. Does 0 satisfy this? Yeah, right? Yeah. 0 as a function will satisfy this. Okay. Does it satisfy the boundary condition?
Yes.
Yeah, it does. Okay. If I had different values, then it wouldn't. But if it's a 0, it would, right? So that'll be the solution, right? Now it turns out that we actually have, we actually run into such kind of situation when we solve partial differential equations. Okay? But in that situation, in that context, this is like the answer you want to avoid. You want to find something that's non-trivial. Okay? So this is called this one is called the trivial solution. Because it's so easy to think. I mean, of course, if nobody tells you that this should be a solution, it's hard to think. But once you see it, it's obvious that this is a solution, right? Yeah. So it's called a trivial solution, and you really want to avoid trivial solutions in order to come up with solutions of a partial differential equation. When we get there, you'll see why. Okay. So this actually became a problem, a separate problem to solve, and they actually have a name, and they're more complicated forms, but I'm just showing you the easiest problem of something's called the Sturm-Liouville problem. Okay. And Sturm-Liouville problem is exactly this. What are the values of lambda such that y double prime plus lambda y equal to 0, y of 0 equal to 0, y of L equal to 0, admits a non-trivial solution, and what are the solutions? Non-trivial solutions. Okay. Now, in addition to this, they actually have some names for these values. So note, lambda is called the eigenvalues. Lambdas are called the eigenvalues. And non-trivial functions are called eigenfunctions. because the name comes from this story that I talked about, the L2 being a vector space, right? And if you have certain vector spaces, this operator on the left side, or actually this negative second derivative operator, is like a matrix. It's like a linear matrix on that vector space. It's an infinite matrix in that vector space. And then you can talk about that matrix's eigenvalues and eigenvectors, but because this is a function space where vectors are actually functions and functions are vectors, you call them eigenfunctions rather than eigenvectors. And that's where this terminology comes from. Okay, and then let me just solve this one. And there are many flavors. This is like the easiest Sturm-Liouville problem, but there are many different kinds of operators in many forms. And then even this one, sometimes this can be replaced by primes. So you might have primes on both sides. And you might have like primes on one side and non-prime there. You might even have like y of 0 plus y prime of 0 equals to 0. There's some other kinds of conditions that can be imposed, and with different boundary conditions you get different answers. So let me just end today's lecture with the specific value of L. So let's say L is equal to 4. Let's try that one. So you have y double prime plus lambda y equals to 0, and then y of 0 equal to 0, y of 4 equal to 0. Find eigenvalues and eigenfunctions. And the solution is so you actually have to check for different types of lambda. So let's say if lambda is positive, let's see what happens. Okay? If lambda is positive, if you plug in EVRX in here, what equation would you get for R? Double prime will give you R squared. Y will give you 1, but there's a lambda there, so it's R squared plus lambda equal to 0. Right? And then if you solve this, you get R squared equals to negative lambda, so that R is equal to plus minus square root of lambda I. So that your solution is e to the lambda ix. Oh, but there's an I in the exponent, so what should really be the solution? Y should equal to. Take a guess. Exactly, right? So we put C1 here, C2 there. All right. Now let's plug in y of 0 equal to 0. But if you plug in 0, you get 0. So if I plug in 0 here, you get 0. But if you plug in 0 here, you get C1 cosine of 0 plus C2 sine of 0. That's 0, so you get 0 equals C1 times 1, giving you C1 as 0. Okay. Next, y of 4 equals to 0. That means I'm plugging in 4 into x, right? So that gives you 0 equals to C1. C1 is 0 already, so I don't have to do C1. And I just get C2 sine of square root of lambda times 4. Yes? Right? So I get C2 equals to 0 over sine square root lambda times 4 equal to 0. Is that what we want?
Yes.
No. Why do we not want this? Because it will be a trivial solution, right? If C1 is 0 and C2 is again 0, look at what the solution is. It'd be 0. So this is exactly not what we want. Okay? So if I don't want this to happen, then what else should happen? For this to not happen, what should happen?
Should we make lambda less than 0?
No. For this to not happen, what should happen? So there's nothing here, right? The 0 should be this. And I need C2 to be not 0. Then what should happen? The other one has to be 0, right? Okay. So we know that it should be, since I don't want this, we really need the sine of square root of lambda times 4 to be 0. Okay. That means square root of lambda times 4 must equal to n pi. Good. You listened well today. Yeah. So we said sine of n pi is 0, right? So it must be n pi. So that square root of lambda must be n pi over 4. So that lambda must be n squared pi squared over 4. Or 16. And if that's the value of lambda, if you plug it back in, you get the non-trivial solution is as y equals to sine n pi over 4x. Oh, not plug in here, but plug in here. We already have C1 as 0, right? C2 is arbitrary, and your sine of square root of lambda x, but square root of lambda is n pi over 4, so you get this. Notice that I'm just setting C2 as 1. Why do I do that? Well, that's because that's how you do it in vector spaces. When you find eigenvectors, you see that for one eigenvalue, there are infinitely many eigenvectors that are multiples of each other. I forgot that some of you didn't take linear algebra, but you know that, right? Eigenvectors, they're linear they're just multiples of each other. You have infinitely many of them, but you just pick one of them, right? So it's the same thing. We have many different solutions, but among them, I'm just choosing the one where C2 equals to 1. Because I just need one non-trivial solution. So when lambda is this value, this will be your non-trivial solution. Okay? But wait, we only did one case, lambda being positive, right? So now what do we have to do? Lambda being negative, but let's do that later. Lambda being 0. Lambda being 0 is, what would that make the differential equation as? Y double prime equal to?
R squared.
Just 0. Or R squared. But you know, you don't do R squared equal to 0 because that's not good, because R squared equal to 0 just gives you R equals to 0 and 0. And then because you have multiplicity, you only get one solution. So it's not going to give you both solutions. So that's not a good idea. Here, you don't want to do it that way. You can just straight up solve this. This is easy enough. How do you solve this? If y double prime is 0, then y prime must be?
X.
1.
A constant, right? Constant, right? Any constant, right? A constant difference.
My bad.
And in that case, y must be cx plus c2, right? Or let's just put a and b. Okay? Ax plus b. Okay, maybe I should just have said a. Yeah. Okay, so if you integrate 0, you get some constant. If you integrate this again, you get ax plus another constant. So that's in general. Now, plug in y of 0 equals to 0. So that gives you a times 0 plus b must be 0, so that gives you b equals to 0. Now plug in y of 4 equals to 0. Well, that gives you a times 4 plus b equals to 0, but b is already 0, so a times 4 is 0. That gives you a equals to 0. All right, so what's our conclusion? What's our conclusion? Was there any way out of getting a non-trivial solution? there was no way out of getting a trivial solution. Trivial solution was the only thing we could get. Okay? So what does that mean? This means that lambda equal to 0 is what? No, is not an eigenvalue. Okay. So there is no eigenvalue at lambda equal to 0. And then still, the last part will be lambda less than 0, right? Now for this one, you could do it and work it out and show that you don't have any eigenvalues, but this will be a general knowledge. So there's a proof generally you can do for the Sturm-Liouville problems that you can never have a negative eigenvalues for. So this is really okay. I wanted to finish early, but because we have to take the quiz too, right? So look, L. So if you have a matrix, something like some matrix A, what's the equation for eigenvectors? So V is an eigenvector of A. What does that mean? Okay. Well, so some of you didn't take linear algebra. That's a pity. But being an eigenvector means A times V equals to lambda times V. That's what an eigenvector is, right? Okay. So those who are nodding, why are you quiet? You should answer, okay? Yeah, but this doesn't look like that. So in order to make this one look like that, what should we do? Negative y double prime equals to lambda y, right? So I just move this to the other side and switch two sides. This is what you have, right? So what this means is that if I apply negative d dx squared to y, that's equal to some multiple of y. And therefore, what we're saying is we're really looking at the eigenvalues of this operator here. And one of the theorems is that the negative second derivative and all the other classes of operators that Sturm-Liouville assigns, those are always a positive semi-definite operators. So that means the eigenvalues can never be negative. Okay? So this one can be skipped because negative d squared dx squared never has negative eigenvalues. Okay? It can never have negative eigenvalues. Sometimes, depending on the endpoint conditions, you might have lambda equal to 0 admitting a non-trivial solution. That happens, but when you have lambda negative, it never happens. So the answer for this question is that the eigenvalues and eigenfunctions are lambda equals to n squared pi squared over 16 with y equals to sine of n pi over 4x, where n goes from 1, 2, 3, and so on. So n cannot be 0 because if n is 0, then lambda equals to 0, and we know that lambda equal to 0 is not an eigenvalue, right? So this is what we have. And there are deeper things that you can talk about this, but that's what we'll start.